Hello, everybody.
Hello.
So welcome to our battery event. So we have a lot of really exciting things to share with you. Christina and the whole development team have really been working on putting together a great solution. Personally, I think it really redefines X-ray diffraction and studying batteries. So, Christina, I mean, what are your thoughts on that side of things?
Yeah, hello. Also from my side, and welcome to our battery day today. We are doing a live event here, XRD and XRM together, and I'm pretty excited with the program we've put together. I look forward to showing you what we have new in store for you today. And of course, we're also really looking forward to hearing what you think about our solutions. And this is one of the reasons why we decided to do this live, is so we can interact with you. Please don't hesitate to talk to us in the chat or in the Q&A.
So with that, Christina, I think that we're ready to learn more about this exciting battery cell.
Our XRD solutions for battery research, I'm going to give you a quick overview what we can do and why you should use XRD for battery research. Of course, the reason we're talking about batteries is because we need a way to store the energy that is produced by energy sources such as renewable, solar and wind power, and somehow make it accessible on the go. Because really we want to take portable devices with us. We want to use electric cars or electric scooters to go to work. And we have battery materials available at the moment, but we really want to make them a little bit better. And the reason we want to make them better is kind of twofold. On the one hand, we want to be competitive with traditional fuel sources. And of course, on the other hand, we have a limited supply of the raw materials. And we want to store more energy in the same amount of materials. We're going to have to improve the specific energy of batteries to get more energy for longer. And at the same time, we have some additional constraints. We want to have the batteries, of course, safe. We want to maybe avoid certain chemical elements due to their toxicity. We want to establish a nice cradle-to-cradle life cycle to make the best out of the limited resources we have available. And of course, the best battery material is only really going to be competitive if it's economical. It needs to be affordable so that it can be in widespread use. For that, also the lifetime is a critical aspect. And it needs to be convenient. Nobody wants to wait for hours for their phone to charge or be without a battery when they went out on a cold day. So we have some battery materials available and they're pretty good and they carry on improving, but really we want to make them even better. So let's take a quick look at a battery on a fundamental level, because that fundamental level is what we need to understand in order to improve the energy storage capacities and the lifetime, etc. So let's look in. What we have inside a battery is actually a series of layers. And these layers are made up of a metal sheet on which we have a cathode, then we have a separator, and then a second metal sheet on which the anode is prepared. And the reason we all roll this up, of course, is in order to increase the amount of cathode and anode of battery we can pack in a small space. If we zoom in a bit more on our cathode material, which is what most people are looking at the moment when it comes to lithium battery research, we find that this cathode is made up of little particles, crystallites. That's maybe a powder that's been prepared as a slurry to generate this layer on your battery. And of course, these crystallites on a fundamental level, on an atomic scale, are made of an ordered arrangement of atoms, the crystal structure. And of course, this crystal structure varies for the different cathode materials. And when we're using X-ray diffraction, it is this crystal structure that gives us the fingerprint of the different materials. So you can see very easily for different cathode materials, we can directly distinguish them using X-ray diffraction because they have a different signature. But not only that, the crystal structure here gives rise to a specific diffraction profile. If the structure changes, maybe because the lithium was removed from in between these layers, and maybe the layers moved a little bit closer to each other, the signature in the diffraction profile will change. Likewise, if we insert lithium into these channels or remove it, these octahedra might rearrange a little bit, or maybe more dramatically, and this will affect the lithium-ion pathways, again, affecting directly the diffraction pattern. So this relation between diffraction pattern and crystal structure, and the relationship between crystal structure and then the performance of the battery, is the reason we're using X-ray diffraction to study these materials. Now, if you want to do XRD to look at batteries, what do you need? Well, you need a battery cell. And typically what we do with X-ray diffraction is we have some sort of dedicated battery cell for XRD in order to really improve the signal and get the best information. This battery cell you fill in the glove box with maybe the new cathode material you've synthesized, and you put it into your diffractometer just like you would put any normal powder sample. You hook up your battery cell to a potentiostat because really what we want to look at is the charge and the discharge behavior, the different cycling behavior. And in order to do that, we've set up a nice control system which allows you to do simultaneous XRD and electrochemistry experiments and to control them through a common interface. And lastly, of course, the data generated by your experiment will need to be analyzed. And for that, we use our EVA and Diffractopa softwares, which don't just allow individual analysis of individual data sets, which can be very time-consuming if you're looking at hundreds of data sets from a cycling experiment, but they can really analyze structures in a batch format or with using cluster analysis. And then you arrive at your crystal structure, and analyzing this can help you again understand the battery performance and improve further the materials. I'm not going to go into any more detail because Jean-Noel Chotard will talk about the battery cell, and he will also share some results from his own research with you in about half an hour. And then later today, Dennis Becker will give a live demo from our lab here in Karlsruhe, and he will really look at the integration of the battery cell and the potentiostat in our diffractometer and show you the workflow that's required to do these kind of experiments. So John, this is all from me, just for a start, and back to you.
Great. So now we're going to bring on another one of our experts, Norman Schott. So
hello.
So from Christina, what we are seeing there, right, is a lot of this more atomic scaled things. So very tiny scale, but very important, right, in understanding those fundamental material properties. Now, switching over to Norman, we're going to look at a technique, X-ray microscopy, and that is kind of a bit of a newer technique to a lot of materials people, right, Norman?
Yes, indeed, because this technology gives you the opportunity to analyze your sample in a 3D volume. So typical microscopy, looking only on the 2D surface that you can see with your eyes, we use X-rays to pass through our samples and reconstruct these projection to work on the 3D volume data to inspect your samples for cracks, inclusions, voids, and how these technology function, I will show you in my presentation.
Okay, and one question. So I've heard of computed tomography or CT that they use at a hospital and such, and I've heard that a technique like this is often referred to as like a micro CT technology.
Yeah, indeed, these big owl-shaped systems that you see in the hospital where you have a broken bone or some tumor or injuries in your body. These technologies is good for you because the resolution is in half of millimeter. It's enough to see if a bone is broken or whatever, but to see little details up to the 0.5 micron, you need something special. And our systems are capable to resolve details up to half of a millimeter, micrometer.
And you actually have the power. I mean, a CT, a medical one, when I think of that, it's shooting through fairly soft tissue. But I mean, here we're talking about sometimes metals, right? And we might even talk about ceramics and things like that. This technology you can actually see in these harder materials?
Yes, of course. Of course, it depends on the shape, but on my presentation, I have also some application examples and I show you what you can expect from which kind of samples.
All right, great. So with that, maybe let's head right into that presentation.
Thank you. So hello, welcome also from my side. My name is Chotard, and I'm the expert for XRM technology. So I will show you how this XRM technology works and what is the output, and of course, for what you can use these data volumes to increase your R&D work or quality control. So at first, we need a tube, an X-ray tube, and on the opposite side, we need a detector. And in between, we place your sample. And if we turn on the X-rays, we will see a 2D projection on our detector. And on this 2D projection, we will see an image, how your sample will look like through the point of view from an X-ray. And if we are now turning your sample from 0 to 360 degrees to grab images from different perspectives, we can reconstruct a 3D volume. And as soon as we have a 3D volume of your data, we can analyze the inner structure. And before I show you the application examples, I want to introduce the 3D data to you, because this is a little bit special and a little bit new, because here we have three-dimensional pixels, not an image. A normal image has 2D dimensional pixels, but here we talk about 3D data, and our data sets made from voxels. And a voxel is a three-dimensional pixel, and it has two important information. The first important information is the voxel size. So you will see later some numbers. Let's say we made a scan with a resolution of 10 micron. Then I mean that the voxel has an edge length by 10 by 10 by 10 micrometer. So this is a resolution. This is the first important information of these voxels. The second information is the gray value, because we can only inspect the differences in density. So as an example, when we have a sample made from plastic, aluminium, and we put it in a scanner and take a look on the results, we will see different gray values. Aluminium will have the highest gray value because it is the highest density material inside the scan. Air will have the lowest density because air has really no density, and in the middle will be the plastic. So here we see a 2D slice of a CT scan, and you will notice that we have different kind of gray values. This is a rock sample, and you will see the black spots inside the rock that are air inclusions, and you will see that the grains has different densities because it has different gray values. So before we take actually look to the examples, let's see the list of what you can do with this data sets. Of course, the easiest form to analyze is a visual inspection to see if the sample has cracks, has broken parts or loose parts. Then we can analyze the pores or the inclusions. We can analyze the thickness of layers, of gluing, of welding, of brassing. And if your sample contains fibers, like a glass fiber or a carbon fiber sample, we can calculate the orientation of each single fiber. We can also do a cut comparison. If your constructor department has a cut file from your sample, we can scan your actual sample and compare it to the cut file to see where it's different. So our first example is a button cell, and we are seeing here is an anode, in the bottom area is a cathode, and in the middle is a separator. And what we can see on these data set is, of course, metal housing. We can see that the anode contains high dense particles because of the high gravity, also some air inclusions and low dense grains. The cathode has a massive crack, and all these features we can analyze. You can see it here in the 3D view that we have the blue volume is a crack, and the yellow points here are the high density inclusions. We can calculate the shape, the amount, and of course the distribution. This gives you an overview what the results can look like. Of course, colorful images are nice for this kind of presentation, but also a CVS file for Excel can be in output. The next example is a normal round cell. Here we can see the single layers. We can see the cathode, the anode, and in between the separator. We can analyze it, that everything goes well by the manufacturing process. We can also analyze the thickness of each layer. Here, green means everything is in tolerance. When there will be a part that is too thin or too thick, the color will change to blue to thin or red to thick. So this is a really quick method to check if the layer is okay, and also if this is a method to check in the whole battery if the layer is okay. The second, or the most big benefit of having an XRM system is this is a non-destructive testing. So you can scan this battery and do some tests afterwards and test it again. So we cut this battery only on the computer, not in real life. So this is a non-destructive testing. Here we have an example for a defective battery. We can see clearly that things going wrong here. We have some bending layers and also some completely destroyed layers where also the separator is destroyed. So this battery has clearly a malfunction. And if we scan it directly after the manufacturing process, we can say, okay, this defect happened via the manufacturing process, or maybe it's happened later with a charge or a discharge cycle. So on this resolution, we can see clearly the single layers, but not the material of the layers. To do this, we need to increase our resolution. In this this example, up to 0.3 micrometer. And here we can analyze the single grain. So here we have two different product methods, A and B, and we can see easily and clearly that A contains smaller grains and B bigger grains. Also, the shape is different. B has nice round shapes and A some kind of free form. So we can analyze these different grain types. We can analyze the shape, the size, amount, and also what is really important to know is the space in between. So we can calculate the pore distribution here. So this gives you a good overview what is possible, what you can expect from a 3D analytic instrument like a XRM system. You will have later the opportunity to see a live demo from my colleague Stefan in the booth. So he will perform a scan for you to show how easy it is to use such a system.
All right, great. Thank you, Norman. We had one question come up during your presentation, and that was, how long was the scan on the cylindrical battery?
This scan was really quick. The battery has a diameter of 20 millimeter, and this scan was 45 minutes, roughly.
Okay, and is that pretty common for one of these X-ray microscope measurements?
Yeah, for XRM, you have to decide, because quality and time is always linked together. If you want to have a really nice, high quality scan, you have to invest a little bit more time. If low quality is enough to answer your question for the sample, then you can go down with the scan time. So it's always a trade-off between time and quality.
Okay, so I'm going to bring Christina back also. And maybe what we could talk a little bit about here is the importance of maybe both of these techniques. What is in their complementary, nature of having both access to microstructure and macrostructural data? So maybe we start with Christina on the smaller scale.
Yeah, certainly. I think what we're doing with XRD is we're looking on the atomic scale. So we're looking really at the changes in the structure on a fundamental level. And this means also, to some degree, the understanding we gain from XRD is a fundamental understanding of the changes to the structure of the reactions taking place during the charge and discharge. We would, of course, love to do XRD on a real battery and really get this local information, combine XRD and XRM. But I think at this moment in time, this is constrained to synchrotron sources. So in the lab, we're going to have to use both techniques independently to tie these information together.
Okay, so here we're X-ray diffraction. We're working on kind of the angstrom scale, right? We're working on that atomic scale. Now, Norman, to say the complementary side of thing, that macro, what are we talking about length scales?
So the state of art is at the moment 0.5 micrometer. This is at the moment the highest possible resolution we can go down. Of course, there existing also other systems like a synchrotron, but then we don't speak about a affordable system for your lab. So the state of art for your lab is at the moment 0.5 micrometer. And
okay.
Yeah.
And that's for the little bit larger type units, right? There's also the benchtop units, and those are more in that, a few micron scale, right?
So our flagship model has these special microfocus tube. Our benchtop systems is limited up to 5 micrometer resolution, but on the benefit of such a system is it's way more smaller, it's a little bit cheaper also, and it's easier to use. So you can decide to go for the highest possible resolution or to a small tabletop system.
All right, and we had a question actually that was coming in kind of on this length scale idea about TEM, about is this method a TEM? Well, I mean, I guess we hear from length scale that TEM kind of sits in the middle of this, right? We have the XRD hitting on that subatomic almost scale, XRM a little bit larger, TEM is in that nanometer scale.
Yes, and of course the biggest benefit of XRM technology is that you're working on the volume data. So with the TEM, you only have a surface that you're scanning a little bit in depth also, but with XRM, you're getting through your whole sample. So you have a volume data, and then you are able to cut your sample digital on your computer. Like when you took a knife and cut your battery right on your table. You can do this a little bit more safety on the computer.
So on that note, I guess, Christina, with X-ray diffraction, we're going to talk about a battery cell, but is there like exorbitant sample preparation? I know, TEM, you typically have to grind it down and like really make this thing atomically thin and such. Anything like that for X-ray diffraction?
Yeah, so maybe one point I want to make, and then I'll comment on your question, is I think the challenge really we have with batteries, they're real life systems, right? They have engineering challenges, they have challenges on the chemistry side, and I think we really have to have a multi-pronged approach to get down and understand really the basics and get to better devices. And then coming to your question, John, thank you. In terms of sample preparation, what we're typically looking at for powder diffraction is you would want to have a powder, you put that in your diffractometer, so you maybe have some sample grinding or some sample milling that you want to do beforehand. With batteries, what we normally do is you would prepare your battery, but it depends what you want to look at. So if you want to look at just the cathode material, you would look at a powder. Presumably, this is what comes out of your synthesis. So you drop that into a sample holder, maybe one that's airtight, and you measure that in your diffractometer. It's pretty straightforward. If you want to look at battery materials in an assembled cell, then you would assemble your battery cell. Again, you would maybe use your powder. So you drop your powder into, for example, this cell from Amiens. You could also have a slurry, so your powder in some sort of solution. And then you would sandwich the cathode with the separator. Typically, that's just like a glass fiber mesh, and then the anode, and then like close off the cell. So I would say, because the preparation of the cathode, anode, and the entire battery cell is typically done in a glove box, it's a little bit more involved because you're in this glove box environment. But in actual terms of diffraction experiment, it's pretty straightforward.
Okay, so yeah, I mean, pretty much sounds aligned. If you're a typical battery type lab, this is the way you prepare most cells, and you're going to be good. Now, we've had this question come a few times, so I just want to be very, very clear on it. The highest resolution attainable with the X-ray microscope. So half a micron, 500 nanometers, right, Norman?
Yeah. Yes. So 500 nanometer is a state of art for XRM systems at the moment. And yeah, we saw.
Yep. And by the way, if anybody's interested in how that resolution, what's limiting resolutions, things like that, we have a video on YouTube about resolution in X-ray microscopy and what comes into that effect. Mm-hmm. There was a question about how do we see inside? And I know, Norman, you had kind of shown that in your presentation. So just to give everybody that quick summary, it's basically we're doing a whole bunch of transmission X-rays and then we're doing them at different rotation angles. We have an algorithm that combines it into the imaging. Let's go with one more question here on the X-ray microscope. Size limitations in terms of the material itself.
Of course. There is a limitation because we have to penetrate the whole sample. The system is shielded with lead, and for the most powerful system in our product line, it's 8mm lead. So this is clearly the limitation of what we can penetrate. For battery means this a pouch cell with a length of 100mm is the limit for our systems, because then the material is so thick that the X-ray can't get through. So 100mm pouch cell is for our system the limitation.
All right, great. Thank you. And so with that, we're going to move on, try to keep on schedule here. Christina, so now we're going to bring on our colleague from France, Jean-Noel, right?
Yeah, exactly. So what we're going to do is we're going to have two parts, in fact. Oh, hello, Jean-Noel. Nice to see you.
Hello.
So we're very
live from Barcelona.
Live from Barcelona, indeed. I think we're very international today with all the different shooting locations. And in fact, Jean-Noel, we visited you in the summer to take a look at your lab, and we took a little video to give people really a nice insight into what you're doing there. So I suggest we start with that.
Hello, my name is Jean-Noel Chotard. I'm associate professor in Amiens at the UPGV, Université de Picardie-Jules Verne. And more specifically, I'm working at the LRCS, Laboratoire de réactivité et de chimie des solides. We are here in our building in Amiens, the so-called hub of energy, where we are working on energy storage and conversion. So it includes battery systems, cathodes, anodes, electrolytes, as well as photovoltaic materials and hydrogen storage materials. We've been working on this type of research for more than 20 years now, and we acquired some good expertise, especially on characterization of operando measurements, and more specifically on XRD measurements during operation of our materials. My main research are dedicated on the synthesis and characterization of new cathode materials, and specifically in the sodium-based materials. To do so, we have to develop new electrochemical cells which allow us to measure at the same time the electrochemical properties of our materials as well as the X-ray diffraction patterns in order to see and to evaluate the change of the crystal structures during the charge and discharge of our materials. Our lab is developing electrochemical cells for more than 15 years now. So this one is one of the first cells that we ever developed in the lab. So it was mainly dedicated to reflection geometry diffractometers. Then we wanted to be able to measure using transmission geometry, and especially at the synchrotron radiation source. So we developed new plunger, as you can see here, with a hole inside, allowing X-ray diffraction beam to go through and diffracting the battery inside the cell. Later on, we continue to develop cells, and as you can see now, we were able to develop a much more compact cell and very versatile, because it can be used either in reflection geometry using this screw here, but just by changing this screw and using another one which has a hole in it and another window, we can use it in transmission geometry, and we can study materials in transmission mode. Using our new TXS diffractometer, we can go through easily aluminum windows, so we don't have to use any more beryllium. And finally, we can also use glassy carbon windows, as you can see here, this tiny little black window here, in transmission geometry. And thanks to this new window, we can get rid of most of the intensity peaks, most of the impurity peaks coming from the cell. So our diffraction room is equipped with 5 different diffractometers. The first one here is the D4, mainly dedicated for routine measurements and phase identification. It's very convenient because we can run different samples one after another, and for an extensive use, that's very convenient. The second one is a D8 equipped with a molybdenum source together with a gobble mirror. So as you can see here, this one is in the transmission geometry, and we can fit inside one of our electrochemical cells in order to perform at the same time electrochemistry measurements together with XRD measurements and check the crystal structure evolution as a function of the charge. The third one here is also a D8, but equipped with a copper radiation and mostly dedicated for regular Rietveld refinements, high temperature measurements, and as well as operando measurements, just like the previous one. The fourth one is a single crystal diffractometer. This time we have a microfocus source with a molybdenum radiation, and the detector here is a photon 100. As you can see, we can also perform low and high temperature measurements thanks to the cryo system. And last but not least, our new diffractometer. This one is a D8 Discover, equipped with a high brilliance rotating anode source. And together with the high efficiency of the Dectris detector, we are able to perform diffraction in less than a minute. So our new D8 Discover diffractometer is equipped with a high brilliance rotating anode source, a dedicated optics, which is focusing on the detector for a high resolution. And we also have a specially designed stage for our new hexagonal cell here, our new electrochemical cells, which allow us to move along X, Y, and Z to do mappings on the electrode and check if the electrodes are still homogeneous during the cycling or not. And finally, we have this Dectris detector, which allow us to do ultra-fast measurements in less than a minute. So a very interesting feature about this new diffractometer is that we can do very fast measurements because it combines both the high brilliance of the rotating anode and the high efficiency of the new Dectris detector. Moreover, I can put my cell wherever I want because I can move along X and Y axis to center the cell wherever I want using the commander here. And I can do a snapshot. So I can position my detector, the middle of my detector at about 14 degrees to theta. And thanks to the wide aperture of the detector, I'm able to measure from about 7 degrees to theta up to 22 degrees to theta using the molybdenum radiation, which is quite a large Q range. So using snapshot, I can do fast measurements with high quality data. And I can repeat that during the cycling of my batteries to see in real time how the cell parameters of my materials are evolving. So the snapshots allow us to stay at the same place and collect data in a very fast way. So we can see live the buy rings popping up on the screen, which will then be integrated using EVA. So using EVA, we can see here two different patterns which have been measured. The black one has been measured in a minute on the very same material which is running right now into the diffractometer. And the red pattern has been measured within 20 minutes. So obviously, in 20 minutes, the gain in terms of noise is very, very nice, very big. But still, we can see that the peak here, even measured within a minute in black, are well defined with a nice intensity ratio of the noise and allowing us to do at least profile matching of our powder patterns and checking the evolution of the cell parameters in a very fast way. So as I just said previously, we can measure a lot of different powder patterns one after another using the snapshots mode. And here is an example that on the same material, this is a classical NMC cathode material. And we can see here the evolution of the 00L lines as a function of the cycling of the material. So we can follow in a very short time and scale the evolution of the material. So materials can be cycled in very fast way, such as one full charge within 10 minutes. So if we want to do that, we need to be able to measure very quickly our powder patterns. And thanks to this device, that's something we can do now here at home, and we don't have to go to every time to the synchrotron to perform this kind of experiments.
Okay, so as you can see in our lab in Amiens, we are developing cells for operando measurements. And that's something we've been doing for more than 15 years now. And we are trying to improve things year after year. So I will try to show you some flavor of what we can do in the lab. So doing operando measurements is obviously something very important for the battery community because we want to check what's going on inside our battery material during the charge and the discharge. That's something we can do easily in labs with lab diffractometers. And the only thing is that it takes something like 30 to 60 minutes per pattern. So if we don't want to have a too big change in the chemical stoichiometry of our material during the collection of the data, we need to go very slowly. But I mean, cells they do exist, and we can do very nice measurements like that. If we want to go faster, we need to go to the synchrotron, but we can't go to the synchrotron every day. And even if we have good relationships with the beamline scientists over there, it's just not possible. Still, we can do it, and you can see here that this cell has been modified to work in transmission geometry. So this is in France at the Soleil synchrotron, and this is in Alba, in Barcelona. And you can see the cell right here also in transmission geometry, working also at different temperature. Of course, using the synchrotron radiation, we have the benefit of the very high resolution and very high brilliance, and we can acquire very high quality pattern within a few seconds. Like we can see here, it's one pattern every 30 seconds. We are also developing cells for neutron diffraction, which brings some new challenges in terms of quantity of materials and also absorption of the material. So we are using here titanium zirconium alloy, which is basically a zero matrix for the neutrons. And here again, we've been able to study the charge and discharge of different materials, and that's just one of the different examples that we did. And we can do Rietveld refinements and follow the cell parameters evolution as well as the lithium occupancy and so on in those materials. Of course, we are not the only one doing such cells, but mainly I would say that efforts are dedicated to large-scale facilities, while we are trying to do that also for the lab. So we need new tools for this operando measurements, because what we want to do is to be able to go much faster. And we want to be able to study materials which can be cycled in a few minutes. So instead of cycling at C/20, so one full charge in 20 hours, we want to be able to do that in 10, 12 minutes. And from a more fundamental point of view, we want also to study what is going on when you are out of equilibrium, because when you go slowly, you are always at equilibrium stage, but when you go fast, things might be slightly different. And we wish also to be able to study all solid-state batteries, which means that we need to go through the whole battery stack, and that's also quite challenging with conventional source. So in the lab, we purchased a few years ago, 2 years ago, a D8 Discover equipped with a rotating anode that you can see here. And a closer view there. So it's a molybdenum rotating anode, and we have dedicated optics in order to focus the beam not on the sample, which is there in the middle, but on the detector to have a higher resolution. So we have a Dectris detector, which allows us to do snapshots when we do the collection of the data. And on top of that, we have a stage, XYZ stage, which allow us to do mappings on the electrodes, and also that it helps a lot for centering the cell itself at the beginning of the experiment. So how does it work? Well, it's a simple, I would say simple transmission geometry. So your X-rays are coming from here. You are going through your material, and then your detector, you can make a snapshot and go to another place, make another snapshot, and so on. You can also do, by the way, just a continuous scan if you want to, but because of the low wavelengths and the quite large aperture of the detector, we can collect just in one image quite a lot of data already. So it makes things much faster. Once you have the data, you can just merge them together and do the integration, and you end up with your, let's say, regular 2D powder pattern. So to do so, we are developing new cells, and we are always trying to improve the design of our cells. And that's what we can do right now. So if we compare that to what we used to do before, that the original cells that we've been working with for many years now, and now you can see that we succeeded to make it much more compact and light, much lighter. It's also quite versatile because we can easily change the windows. We can use the classical beryllium windows, but we can also use aluminum or glassy carbon windows. And by changing just the ending part of the cell, this kind of screws that you can see here, we can use this cell either in reflection mode or transmission mode. And we are also developing dedicated designs, and this one, for instance, is used for a very small beam, like we can have with the rotating anode diffractometer, because it's just a 0.8 millimeter wide beam, and in that case, we can use much smaller windows, which are also more resistant. And another thing that we are trying to do is to try to do temperature-controlled measurements. So this is still in the development stage, but the first trials that we've done are quite encouraging, and we hope that we will be able to do a nice temperature control measurement very soon. This is very important for all solid-state batteries, for instance, which requires typically 100 degrees or even more to have a good ionic conductivity regarding the solid electrolyte. So we have to check also the electrochemistry of our cell, and I'm comparing here the galvanostatic curve of NMC material, so lithium, nickel, manganese, cobalt oxide. So maybe it's not that visible, but you have a black, a red, and a blue curve right here. And the black was measured with a regular coin cell, and the red was measured with the old cell that you saw previously, the big one, and the blue line has been measured with the hexagonal cell. And as you can see, they are all one on top of the other, which means that our electrochemistry is really reliable from one cell to the other. So we want to measure fast, but how fast is fast? So we did several trials, and we've been able to measure from 60 seconds down to 5 seconds, as you can see here with the black powder pattern. So of course, if you superimpose everything, we are losing quite a lot of intensities when the time is decreasing. But if we normalize, we see that it's much more noisy when you have just a 5-second scan. But still, we can definitely see the position of the peaks, and we are able to follow the peak position changes during the cycling. And it's just in a 5-second scan. So that's really, really, really fast. So this will help us to study the high cycling rate materials, of course, but also it might help to identify the new insertion and de-insertion mechanism. When we go so fast, we are expecting to see some metastable phases appearing during the cycling. So as an example, you can see here the operando measurement on NMC material. And just for this purpose here, where I was cycling quite slowly, it was a cycling rate of C/10. So I could afford to spend like 20 minutes per scan. This is here the corresponding electrochemical curve, and usually we try to plot it this way so we can see what's going on during the charge and what's going on during the discharge. And if we look closer, we can clearly see the different changes of the peak position during the cycling of the battery. So that's at low angle here, that's the 003 reflection, and that's some more complex behaviors that you can see. Obviously, we have some straight lines here, some peaks which are not changing. Those peaks are due to either the lithium anode, or the windows. If we use aluminium or beryllium, for instance, we will obviously have some straight lines during the measurements. So we can, of course, do profile matching at least of those phases, and that's one of the examples. So we can see in black the evolution here of the A parameter of NMC, and here on the right side that the evolution of the C parameter. And it turns out that, in fact, at the end of the charge, we have a biphasic domain, and you can see in red the cell parameters of the second phase, which was identified during the cycling. But we want to go fast, so 20 minutes per scan is pretty long. So we went down to 2 minutes per scan with a C rate of 1C, so 1 charge in 1 hour. And then we even went faster with a 5C C rate, which means a charge in 12 minutes. And for that, we did a 12-second scan, 12-second per scan measurements. So of course, intensities are much lower, but still we are able to see very clearly the evolution of the cell parameters during these very fast scans within 20 seconds, which was really not possible before with regular reflection diffractometers. Otherwise, you need to go to the synchrotron. So another thing that we want to do is to study the all solid-state batteries, and that's one of the examples here. So here again, we have NMC material mixed with argyrodite solid electrolyte. We have a composite electrode. In the middle, you have solid electrolyte, argyrodite, and down here, then we have a lithium anode. If we look at the cross-section, somehow we have something like this. So that's just the stacking of the different layers, and all together we have something like about 700 micrometer up to 1 millimeter thick full battery. So studying this is also quite challenging, and if we use reflection mode, we will probably see only one side of the stack of the battery. So either we will study the positive electrode, or if we flip it, we will study the negative electrode. But if we use the transmission mode, we will be able to study the whole battery. So obviously, once again, the synchrotron and neutron facilities are the best tools that we can dream of, but once again, it's not easy to go there, and we want to do as much as we can from home. So with our new diffractometer, and thanks to the high energy, we can go through those materials, and we can study this kind of material. So here is some example. We first tried to measure different pellets of different thicknesses, and you have here in black a pellet of 200 micrometer, in red 500 micrometer, and finally in blue 1.25 millimeter thick electrodes. And those measurements were done using 3 snapshots, so that's 60 seconds per snapshot, which is pretty fast too. So obviously, the thicker the electrode, the more we will have, the more it will absorb. But still, we are really able to have pretty nice diffraction patterns within a very, very short time. And we applied that also to studying all solid-state batteries and cycling them directly also into the diffractometer. So that's what we did here. And you have at the top right here the galvanostatic curve of this material. And as you can see, only a few peaks are moving right here and there. That's the active material. And in fact, all the other peaks belong either to the cell itself, the windows, or the solid electrolyte. And in fact, we don't want the solid electrolyte to move because this material should not be electrochemically active. So during the cycling, this should not move at all. And this is what we observed, so we were quite happy about that. But some peaks are moving, and if we look more closely to them, And if we do a contour plot of that, we can here also see the evolution of the cell parameters and of the peaks, diffracted peaks. And you notice that the evolution is a bit different from what we can have with regular liquid electrolyte, but it's also because the mechanism are much different within a solid state battery. So that's quite the end of this presentation. So with our new device, we have a high energy and a high flux, which allows us to make very fast measurements. So we can definitely measure powder patterns in less than a minute. Thanks to our new cells that we can use either in reflection or transmission geometry. And soon, hopefully, as a function of temperature, we can do operando measurements. And finally, this will help us also to study all solid-state batteries. So thank you for your attention.
Yes, thank you very much for the nice presentation, Jean-Noel. I enjoyed it quite a bit.
Yeah, it was a great presentation. In fact, it's inspired quite a few questions have come in. So in terms of the schedule, by the way, there is a break right now, but we're going to go ahead and maybe answer these questions. So the first question is the window sizes. What are we talking about on window sizes on the input side and then on the output side?
You mean in the cell itself?
Yes.
So the output window, so it depends, it can be changed, but the typical one is about 18 millimeter wide at the top, and it's 14 millimeter at the bottom. So, I mean, the entrance is at 14 millimeter and the outside output is 18 millimeter wide. But we can decrease that as well, especially if we use glassy carbon windows, because they can be broken very easily. And in that case, either you increase very much the thickness of your window, but it will absorb a lot, or you decrease it a lot to make it more rigid. And that's what we did. So in one of the slides, you could see a very tiny window. So this one is just 5 millimeter wide, which is suitable for the diffractometer we have, because once again, the beam size is 0.8 millimeter. It won't be suitable for a regular D8 with a very wide beam, but for very narrow beam, very useful.
Okay, and then the next question that came in is there any benefit for in operando single crystal X-ray diffraction style experiments?
Single crystal operando diffraction experiment?
Yes.
I'm not aware of such measurements. I tried, but that's really not easy to do. And I would be happy to have some input about that. If someone can do that, wow, that's really cool. I wish I could do that, but I never did it. I never succeeded to cycle one single crystal. I wish I could.
All right, and in the next question, what are some typical scan times, say in particular the Mali type work and that? I know you had said it during the presentation, but maybe if we could go over that again.
So it really depends on the C rate you want to use. So if you have time, you can spend 1 hour per scan if you want. I mean, if you are cycling very slowly your battery, then you can go very slowly as well for collecting your data, and you will have gorgeous statistic. But if you want to cycle very quickly, like 5C, 10C, then you need to do snapshots, and for that you need to collect within 10 seconds, which is possible. Of course, the statistic will be will drop drastically, but so you won't expect to do read-vet refinement with a 5-second scan, that's for sure. But still, you will see the evolution of the peaks and appearance of the different phases.
Okay, so for that quick analysis,
it ranges from 5 seconds to whatever you want.
Okay. Okay, so for the quick analysis, you said somewhere in the order of maybe 5 seconds, 20 seconds. If you wanted that read felt, what would you recommend there for the dwell times on those frames?
If you really want read velts, I think you should go over 5 minutes probably per scan, which is already pretty good. It will obviously also depend on the crystallinity of your material, the quality of your sample, and how well it diffracts and so on, of course.
Yeah.
Okay.
I think this is a really important point, maybe to butt in. You have a really nice big detector, right? So you can really capture the diffraction pattern probably in one go, and you can do pretty good snapshots. And I think one thing we see very often is when somebody asks, how long do I have to measure? The answer is so often it depends. Because as you said, maybe your statistics should be good. Maybe you need to cover a big range. Maybe you actually pack lots of material into your cell so the transmission will be less. So it's actually pretty hard to give one number and say, this is the time you should aim for.
Absolutely. There is no typical answer for that. It will depend what you are stacking. If you are going through, if we are talking about the all solid state batteries, then you are going through almost 1 millimeter thick electrodes, which is very, very thick. So, well, it really depends.
Yes.
So part of this time then is going to be detectors. And so we did have a question about that. Now, in your experiment, what type of detector were you using?
So with the rotating anode diffractometer, it's a Dectris 500K detector. And I mean, specially designed for this kind of energies. We are using molybdenum energies. And well, it's pretty convenient and measuring pretty fast what we want to measure. So far, we are quite happy about it.
All right. So then
I'm not a specialist of detectors, so I'm maybe not the best one for answering that. But.
Yeah. So I mean, speaking of specialists in detectors, Christina, now Eiger is a very high-end detector, I would say. And does that mean that it's a preclude, like you have to have such a detector in order to do these types of experiments?
No, absolutely not. I mean, what is nice about the large detector is that you can do snapshot modes, really covering a large space of your diffraction pattern in one single shot. But of course, you can also do scans, both in transmission as well as in reflection geometry. And then if you use, for example, the lynx-eye detector or the lynx-eye XCT, that may be actually giving you a slight benefit if you're working maybe in reflection geometry, because you can cut out the fluorescence coming from your transition metals. So it really depends a little bit. What's the best? It might depend on your setup and on your sample.
And with these linear detectors, we're taking those scan times from being, the 5-10 seconds up to just a few minutes, right? We're not talking hours.
Yeah. No, for sure not.
Okay. Now, the window materials themselves, so they appear fairly thin, and we were talking about beryllium, which sometimes people, they get a little excited about. What's the durability of these materials?
Well, if you're talking about beryllium, this can be, it depends how you use it and how you clean it and how you protect it. Beryllium doesn't like to be oxidized. So if you want to go to very high potential, like something above 4 volts versus lithium, then you will have to protect it with a thin foil of aluminum, for instance. Otherwise, you might damage your beryllium window for sure, and pretty quickly. I mean, it won't be within one experiment, but after a few experiments, you might see that you are starting to damage your window.
Okay. And that beryllium, that would be, we call that kind of the highest end window that gives you the highest transmission and such like that. If somebody was starting out in this, would you recommend maybe that they went with something more like the aluminum window to start with, use that on a routine basis, use the beryllium one, on the other hand, for those special samples?
Yeah, well, aluminum works well. You can use it for the positive side. You should not use it for the negative side because it will make alloys with lithium. But at the positive side, for sure, you can use aluminum as long as you have a high penetrating source. If you do that with copper, it won't work because if you use copper reflection mode, then that may be not the best idea. But if you use molybdenum in transmission mode, then no problem.
All right.
And it's cheaper and safer, of course.
Okay. And all these windows, I mean, the cell, of course, it is available on from Bruker instruments. Christina, we do offer all the different window type materials. People can get those,
yes.
Right?
Yes.
Okay.
So we're offering the cell that Jean-Noel developed. And what's nice about it, it fits directly into the powder diffraction stage. And you're good to go.
Okay. So maybe one more question here. This is a good one, I think. Angular coverage. So what is your maximum 2 theta you get out of the cell? And then what is your angular coverage that you're getting in a snapshot?
In a snapshot, it's about 14 degrees, but well, actually, it depends how close you are from your sample as well, because right now, I don't have the figures in mind, but I might be at 260 millimeters away from the sample, I guess. And in that configuration, in using molybdenum, I'm covering from 14 degrees. So coming closer, I will cover even more. I mean, in Q space, for sure.
Okay. And that's and they're really balancing resolution and also coverage, right? So there's always that.
The closer you come, the less resolution you will have.
All right, great. Well, I mean, I'd really like to thank you, Jean-Noel. It's very been enlightening. All right, so maybe we give just a few minutes. Maybe let's have just a quick little discussion about some of the stuff that we've learned as people come back over to the stage. So basically, just to summarize, Christina, maybe about this release. So we have a few different components to it. We have the cell. We also have a potentiostat. We have some integration. Maybe you could just give us some summary how all those pieces kind of are working together.
Yeah, I don't want to preempt the demo too much, but so what we are releasing now and what we've released this year is, on the one hand, the battery cell that has been developed in the lab in France, and that Jean-Noel just showed us a bit earlier how he's actually using it for his research. And what's quite nice about the cell, it's reliable. So that means if you are somebody who's synthesizing your own maybe cathode materials, you can take his cell, you can fill in your cathode material, prepare it with the anode and ready for diffraction measurements. And then the cell is airtight, hermetically sealed, so you can really leave it in your diffractometer for hours and days on end and do these kind of cycling experiments. What's also, I think, nice is the cycling side of it. And as I said in the introduction, is you need a potentiostat to drive this charge and discharge of the battery. And there's several ways of doing it. For example, you could just charge your battery at any rate you like, really, and just take snapshots of X-ray diffraction patterns as you do the charging. So you're kind of doing these two experiments in parallel. And the other alternative would be to say, okay, I'm maybe charging my battery to a certain charge state. Maybe I'm expecting some phase transitions. And at this certain charge state, I'll take a pause and I'll take a longer diffraction pattern just to really record a good data set, maybe ready for read-felt refinement. And then you can carry on and take the next charge step and then again, a longer diffraction pattern.
And yeah, correct me if I'm wrong, but this is the first and only diffraction solution to have full control of a potentiostat, right?
Yes. So
that we are aware of.
That we are aware of. So I think this is something which I think we're quite proud of, and we're actually very happy to have this integration, is because you're not just programming your potentiostat, you're programming your diffractometer, you let them run in parallel, and afterwards you're trying to match up the data sets, but you have really control about where you measure in your charge cycle and how long you measure, and maybe you want to combine different scans. So maybe you want to do some rapid snapshots in certain stages and then longer measurements to really get in-depth structural information during other parts. So yeah, I think we're the only one that can do that, who can do that, and we're pretty excited about it. And Dennis, I think you will actually show a little bit as well later how to set this up this kind of experiments.
Yeah, definitely.
Yes, so to now add to the conversation, we are now joined by Dennis Becker, and he is in our Karlsruhe App Lab, so thanks for joining us.
Sure, it's a pleasure.
And so you're going to actually show some of this in action, right, live here?
Yeah, we have something prepared for you here on a D8 Advanced in our App Lab, and I want to show you some things here.
All right, great. So we're going to switch over to you, and if anything comes up, we'll be here in the background.
Okay, sure. All right. So we have prepared here for you a D8 Advanced and a basic powder geometry. And just come a bit closer here, maybe to me, and have a look inside the machine. So simple powder setup. Right now, a powder is mounted, standard powder sample, and I want to switch now to the battery cell. Well, how to do that? I don't even need to change anything on the machine. All I need is here my battery cell that I have already prepared. Consists of 3 parts. You saw a little bit already before. The upper part holds the beryllium window, in this case here. The middle part separates the cathode and the anode, and the lower part is just a plunger to push the cell in. It's tightened with just a few screws, so it's very easy to assemble. With the red cable, we have a connection directly to the upper side of the cell, and the anode is inserted here into the plunger so that we get an electrical contact. For the cell itself, we have a magnetic holder, which is comparable to our powder holder. So all we need to do is plug it in magnetically into the machine. And that's it. And we are already in the battery mode where you can measure a battery. So there is no reconfiguration required here. Let's maybe have a look at the potentiostat, which is also based here inside of the machine. This is an SP50 potentiostat provided by Biologics. And the connection to the machine is also rather simple. You don't need any extra parts. It's connected with a LAN cable for the data transmission to the internal LAN hub. On the back side, it has a power plug. It's a normal cold plug. So nothing fancy here. And on the front side, we have the cable for the battery, where we connect the battery. In our case, since we use a simple two half-cell lithium-ion battery, we have a cathode and an anode cable, and I just show you how to connect it. So the anode we plug directly into the backside of the battery inside the plunger here, plug it back in, and we connect the cathode side with the red cable here. And that's it. And now we're ready to go on the hardware side. Close the door. Okay, the question is now, what do we actually want to do? Let me explain a little bit. So if you follow me here, we have prepared some drawings for you. Let's compare this to a non-ambient experiment, which you might know from a temperature stage. We typically start on a starting temperature at ambient temperature, maybe at 25 degrees Celsius. So we want to know what is the initial state of our material. We not want to see the pattern of the initial state. So we hold this temperature and we perform an XRD scan here as long as we hold this temperature, maybe a 1-hour scan, maybe a 20-minute scan. Then we increase the temperature. We change one of the parameters. And we wait until we have equilibrium again. And again, we will do a long XRD scan. So basically, we are working in a static mode. We change one parameter, we wait, and then we scan. It's of course coordinated, but one parameter has to wait for the other parameter. In a dynamic experiment, we don't want to wait. We want to see what happens while we increase the temperature. So we will split our XRD scan into very small parts. We only scan maybe smaller ranges, but especially we scan only very short times. So maybe we measure just 2-minute scans. So while we are increasing the temperature, we are measuring a lot of small scans so that we can see what is actually happening inside the material while we heat it up. Let's transfer this now to a battery experiment. What might happen in a battery? Flip this one here over. In the battery, we have a bit often more complex things we want to see. As Christina already mentioned, we might have a open circuit voltage where we want to see what is the initial state of the battery, but we also are charging the battery with a constant current, and constantly the structure is changing. But in between, we might want to have a plateau and want to see what is the structure doing in this specific area. So we need to combine dynamic and static experiments. Let's start with a more or less simple static experiment on a battery. We have the initial state of the battery at a low charging state, low voltage, maybe 2 or 3 volts. And we scan here a long XRD scan. We want to see what is the initial state of the battery. Let's take a 1-hour scan so that we have sufficient data quality. And then we start to apply a constant current. So a high current, we're pumping electrons and lithium ions back and forth between, or they are moving from anode to cathode or the other way around, depending on if we're charging or discharging the battery. And while we are charging the battery due to the lithium insertion, we have a change in the structure, and we want to see what this change is. So we are scanning with fast XRD scans again, and are following this trend, this changing parameter, this changing structure. After fully charging the battery, we might want to have a long XRD scan again to see how it looks like fully charged. So we have here already a combination of the static and the dynamic experiment. And we might want to make this a little bit more complex, since there is some specific state, especially when we have charged the battery, like here. At some point, we come to a very high voltage where we cannot increase the voltage anymore. The battery is pretty much at its limit, but still there are some changes happening in the battery. So we want to hold this voltage here in a constant voltage experiment. And while we hold the voltage, the current is decreasing slowly. So we're still in a range where we want to have fast XRD scans, repeating scans, and then we go over into a state of open circuit voltage. Now we want to see what is the final state of the battery. We don't want any structure change anymore, so we can apply a long XRD scan anymore. So it's necessary for the software to allow to have all these complex interactions, to have an interaction between applying a constant voltage, applying a constant current, open circuit voltage where no current is applied. So static and dynamic steps, we are changing back and forth between them. All right.
So Dennis, can you, I don't know if you can hear me.
I can hear you.
And excellent. So what I see now is effectively setting up the instrument is pretty straightforward, right? You have a Bruker kind of setup. You take out your powder sample, you put in your battery sample. Okay, you connect it with the potentiostat, and I can see the potentiostat is inside the diffractometer, and it's also connected to our computer, or how do we establish that connection there?
It's connected to the internal LAN hub of the machine, and this LAN hub is then connected to the computer. So the software recognizes it as a part of the machine.
Okay, and I like your explanation really with the sort of flip chart, the general explanation of the experiment. And I think this is also probably the next thing you're going to show us is how we not just think about these experiments on a piece of paper, but how we actually plan them in our diffract measurement wizard software. Let's take a quick break and see if there's any questions coming in from the audience, maybe that we should take at this point. John, did you see any?
Yeah. So there was one question about the integration of battery cells in general and the history of it with diffraction. And that's a great question. So measuring batteries in a diffractometer is something that's well established, right? So yeah, I mean, many people have it. Bruker has had it for, I mean, I'm guessing, I don't know, Christina, how far back do you think that we've been looking at batteries?
Wow, probably 10 years, maybe. Yeah, probably at least. I mean, it's always been one of those fundamental technologies, but the unique bit again is going to be that full integration from setting the potentiostat in our software, full solution, right? Yeah, and I think another part is really, I think we've had quite a bit of improvement in terms of measurement speed, also with the larger detectors, right? So before, maybe you would go and charge your battery a little bit. Maybe you do it even on the bench. Then you take your cell, bring it to your diffractometer, you measure, then you charge it a bit again, and you kind of go back and forth between those two states. And I think with the larger detectors and the also the efficient 1D detectors, we can really get down to a measurement speed where we can do these things live in situ and in operando. And I think that is really the critical change we've had in the last, let's say, 10 years or so.
And if anybody has any questions, again, just type them in the Q&A on the side. So Dennis, before we had this fully integrated solution where it was writing right into the data files, these numbers, the voltages and the currents and things like that, how would you actually execute one of these measurements on a diffractometer?
Oh, well, that's a good question. You would actually rely quite a little bit on luck. So typically you would program your potentiostat to do something in some software. And then in the diffractometer software, you tell the diffractometer, repeat the scan. And you hope for the best. The scan is still repeated while the potentiostat is running, because beforehand, you didn't know, is my battery charged maybe in an hour? Is it charged in an hour and 10? Is it charged after 50 minutes? So you set something up in software A, which is the diffractometer software. You set something up in software B, which is the potentiostat controlling software, and you just hope that it runs approximately in sync. But now we have an actual communication between these two parts because it's all integrated into software A, which is the diffractometer software, and we have a direct communication between the two parts.
Yeah.
Okay.
Reminds me of non-ambient experiments where you really, the old-fashioned way, you program something, you program the other side, you cross your fingers, and then you do it again because it didn't work out.
Yeah, you're sitting there with like one finger on each keyboard, right? Ready to go.
Right.
Put a long dwell time in, right? So that you can get it in there. So, I mean, this actually, I think this opens up though that idea that you can also do a lot of charge discharging, right? So if you wanted to set it up to charge and then discharge, charge, discharge, charge, discharge, say all night long, collect a scan and see the evolution of the materials over that charge discharging. That's something you could also do, right?
Yeah, absolutely. You can also program a continuous charge and discharge, so you can combine it in any way you want.
All right, great. So with that, again, any questions that pop up, let's make sure to type those in the Q&A. In the meantime, we're going to go back to Dennis, and I think he's going to show us a little bit of the actual software integration side of things.
Yeah, that's true. So we have prepared something on the PC. So if you want to follow me on this side here to the PC, we'll first have a look at the Commander software and how we set all that up. So in the Commander on the left-hand side, we see the instrument settings. We see things like the theta position. We see information about the detector, about the optics. And what is new now, we also see the information about the potentiostat. So you see labeled here as biologic SP50 on the lower left-hand side. We see the mode, which is active. We see applied currents, target voltage, and so on. So we see actually what the potentiostat is doing. Typically, we would like to set up now a rather complex experiment. So this is something we cannot do directly into Commander. We will use the XRD wizard to tell the machine which XRD scan should be performed and what segment or what mode should be applied in the biologic. So let's switch over to the wizard. I have prepared a little bit here already. So on the left-hand side here, a little bit up, you see XRD basic, method 1 and method 2. So I have already prepared two XRD methods. One is a rather long scan and one is a rather short scan, about 2 minutes. And yeah, then let's maybe switch over to what is new here in the wizard. This is the sample environment called multi-technique now. And I'm already here. I see segments, start time, duration, operation. So I see some information, some kind of table where I can put in all these things I want to do. So the first segment is always prepare. So I tell the potentiostat what are my safety limits, and then I can immediately start with the segments I want to apply on the potentiostat. So I have here a drop-down menu and can select between constant current, constant voltage, open circuit voltage, and some more. I want to start now with open circuit voltage because I want to see what is the initial state of the battery. For this, I might want to apply a longer scan. But let's first continue with setting up the potentiostat experiment. So what do we actually want to scan? So open circuit voltage to have the time to see what is the initial state on the battery without applying any external force in form of current or voltage. And let's just add some more segments. So I can put in as many as I need. And let's say the next one should be constant current. I want to start charging my battery. So I will charge it, let's say, with 5 microamps, and I want to charge until I reach something like 4 volts, for example. Now the software is complaining here because I'm outside of a safety limit I've set. So it will even control that I set it up properly. So one of my safety limits was about 1 volt because we are not using a typical lithium-ion battery. We are working with a lithium manganese oxide based material in a water-based electrolyte. So we're actually cycling LMO against LMO. It's nothing fancy, but it's easy for us to work because unfortunately we don't have a glove box available, so we can only work with these more simple materials. I will charge it up to 0.8 volt. After it has been fully charged, I want to have an open circuit step again, so I can see how does the structure look like when it's fully charged. So I have more time for XRD scan and a static mode. And then I, let's say, want to discharge the battery. So I'm using a constant current experiment again with minus 0.005 milliamps or 5 microamps down to minus 0.8 volts. And here I decide I also want to put in a constant voltage experiment, because even though with the current I might have reached the lowest discharge, I still can pump in or pump out a little bit more of the electrons. So let's say I also want to continue into a constant voltage experiment, and you see it will immediately take over the end value of the constant current experiment and put it as the applied voltage for the constant voltage experiment. And I can define what is the end criterion, and here I go down to 1 microamp. So really, if the current is really smoothing out, then I finally finish this experiment. So I can combine many different things here. Let's maybe finish with an open circuit voltage at the end. So the question is now, how do I coordinate all of this with XRD scans? That's rather simple. I just click on the segment where I want to apply an XRD scan, and I click on the flag symbol here, insert measurement, and now I can select which measurement I want to use. So either my long scan, method number 1, or my rather fast scan, method number 2. Like I said in the beginning, for open circuit voltage, we have a static mode. We want to see what is the initial state of the battery, so we'll use the long scan, and the segment is already applied with the duration that this long scan has, about 1 hour. So open circuit voltage will just be applied until this 1 hour scan is over. Now let's go over to the constant current, to my charging step. I again click on the flag symbol, and here I switch to method number 2. Let's have a look now a bit more on the right side. You see here repeat as an option. Of course, I should turn this off for my first method. I don't want to repeat the scan over and over. I just want to have one long scan over this static period. And now I'm in a dynamic experiment with the constant current. It's constantly, the structure is changing. So I want to use these short XRD scans, and I want them to repeat as long as the segment is running. So here I'm enabling this repeat option. And I will do the same as for the second segment. Now here, open circuit voltage again. I want to apply a long scan. And maybe I don't need to go into much more detail. What we really want to show you here is you can completely freely combine whatever you need. And you notice it starts to get a little bit complicated. So if you set an experiment up here and show it to your colleague, he might think, oh, did you maybe miss a step, or where's what now? Don't worry, you can also put in some comment lines. So here I can comment start or initial state. Let's call it initial state. And I can also give it some color, maybe lavender colored. And now I switch over to the constant current experiment where I actually charge the battery. So I will call that charge and make it green. For charging, green is good. Then I'm in the fully charged state. So I will call this one charged ED. And I will also make it again lavender. This is just the color code I like. For lavender, I know this is a static step. For green and yellow, I know it's either charge or discharge. And I can use that system here also. Now discharge and so on. And now it's much easier to understand what I'm actually doing here. And at the end, with the open circuit voltage, I will put in a comment with final, for example. And like this, I can coordinate an experiment. Have any questions come up so far? Maybe I give you a breather here.
Yeah, Dennis, thank you. I think it's actually pretty impressive. The experiments we're looking at are actually quite complex, right? Because we have not just one thing we're controlling, like in a temperature experiment where you just set the temperature, but you may want to control the current. In a different situation, you may want to actually control the voltage. So I think it's actually really nice how you can structure the setup of the experiment and make it more obvious what's going on straight away. And I think the other thing which I really like is how you can just select the different measurement types from the drop-down menu. So I think that is actually pretty neat.
Yeah.
There's
and
one
this whole wizard interface. This actually it's something that's common throughout the diffraction software, right? Or is it just for batteries?
No, this is common for the diffraction software.
Okay, so if you wanted to set up regular powder scans or even stress measurements, things like that, there's a specialized wizard to guide you through that measurement.
Yeah, basically. So you have all the options for setting up the experiments in this same wizard view. So you can control all the parts of the machine inside this this wizard environment.
Okay.
Oh, that's nice. So Dennis, I interrupted you. Sorry about that. Do you want to start this scan and then maybe we take a look at the components, or?
Yeah, absolutely.
Yeah.
So I will not start this scan. This is a bit too complicated, and these are also not the correct settings for this battery. I've prepared a rather simple scan so that we just see what is going on. Sorry, I'm wrong here. What I want to do is constant current applying onto the cell, because in the other experiment we had set up an open circuit voltage with a 1 hour scan. This might be a bit boring. So we want to actually see that the goniometer is running and is coordinated with the potentiostat. So for starting an experiment, you go to Start Jobs. You just select the experiment you have set up, which is my charge here. And I just let generate a result file name. Let's also give it a number 1. And that's basically it. So the software will automatically export your data into a file that you can evaluate later on. So as soon as I started, let's go to the commander. You see everything is grayed out now. Now I don't have the control anymore. The software has the control now. You see in the lower left-hand side for the biologic, it changes the state to constant current. You see applied current. You see the target volt, or you see the actual voltage that we have right now. Something is running, and you see the drives are moving. So let's follow me back to the machine. Hello. Let's have a look at the goniometer. And we see rather slowly, but it's moving. This is about 2-minute scan, and it will repeat this 2-minute scan over and over again until the potentiostat gives the signal that the battery is fully charged, and then it will go into the next segment. For this experiment, of course, there is no next segment, but in another experiment, there might be several more segments, and then this will be applied accordingly, and the diffractometer will automatically go into the XRD measurement method that you have supplied.
All right, great. So we did have a few questions come in, and if anybody has any additional questions, please make sure to type them in. When you do transmission mode, how do you place the cell? Do you put it in upside down? Is the tube on top? What would that look like?
Oh, that's yeah, Christina, please.
Yeah, sorry. No, go ahead. Let's see. I'll complement your answer.
Okay. Well, the typical answer is, as always, it depends. It actually depends on what type of cell you're using. If we're talking about a pouch cell, I would put it on a XYZ stage so that I can also select on which area I want to illuminate. If we're talking about our battery cell here, which is usually used in the reflection mode, we can also use the plunger, which has a hole with a second window, and then we can basically shoot through. So we could either use it in a mode where the tube drives above and the detector below so that we just shoot completely through, or we could also mount it onto an XYZ stage and shoot through it horizontally instead of vertically.
Yeah, the one comment I would maybe add here is keep in mind, if you do transmission experiments, you have several layers inside your cell that you want to shoot through. Yeah. So while we are now working with the copper tube, for the transmission experiment, you very likely want to change to molybdenum X-ray source just to have this harder energy to really transmit through all these different layers in your diffraction in your cell.
And interesting thing that you had mentioned there is a pouch cell. So I guess what you're saying with that comment is that this whole system, though, of the controlled charging and discharging, it's fully compatible with people's own custom cell designs?
Yeah, absolutely. So all the system or the software cares about is that this SP50 potentiostat is connected, because this is controlled. What is then connected on the other side of the SP50, so on the end of this blue and red cable, the software and the machine don't care actually. So you can connect whatever. It can be a pouch cell that you made yourself. It can be our battery cell. It can be anything.
All right. And kind of a related question, probably for Christina, is if somebody really likes this potentiostat and the cell itself, is this something that they would get from Bruker, or is this something they go to someone else to get?
Yeah, so we are an exclusive distributor for the battery cell on behalf of the University of Amiens. So if you like to purchase the battery cell, or if you would like to have the potentiostat integrated in your diffractometer, then yes, you do come to us and we will provide this solution to you.
Okay. Now, this whole controlled integration system, we do have, of course, a lot of users. We have a lot of diffraction users, XRD, or powder as we'd call it. There's also some SC XRD customers out there. And one question coming in is integration with Apex 3 or Apex 4 type software.
Okay, so the Apex software is more on the structure analysis side of single crystals, right? So what we are here is one step before. We are actually in the data acquisition step. And I have to disappoint our single crystal users because the integration of the potentiostat is available for the control software for our X-ray diffractometers, but it's not integrated into the control software of our single crystal diffractometers. So if you want to benefit from this integrated software, then you have to use an XRD software.
And one thing to note too on that is if we look right behind Dennis, you kind of see the design of the enclosure with the blue on the side, the white in the middle. That's what we called our Da Vinci system, right? Released about, 10 years now ago, I think. So
close to 10 years.
Yeah, so if you have one of those, we would call legacy machines, the one that maybe has the top with the accordion style doors and such, then this would not have that full integration with one of those machines going back the 15 years or so. So you need one that kind of has that bluish and white design. So here we go for Dennis. Is it? Let's see here. So I'm going to read the question just as it is, because I think we could take it a few different ways. Is it not recommended to set a rest between the scan?
Rest between the scans. This depends really on what you want to do. In my opinion, personally, I would not set a rest in between because I want to see continuously what is going on. So ideally, I choose a scan time that is shorter or faster than the change that is happening inside the structure. And then I actually don't need to pause in between, because the structure is continuously changing and I want to have the best resolution possible to see this change. So I wouldn't pause in between.
Yeah, I think it depends, right? If you are at this stage where you will reach the equilibrium and maybe you've done your constant voltage charge step to really finish charging your battery. At this stage, maybe if you do want to wait for your battery to equilibrate and then measure a long diffraction pattern, then maybe you can of course program a delay between the last step and the beginning of the diffraction measurement. But in general, as Dennis said, if you're trying to follow processes that are going on while you're charging, you want to be quick, you want to measure really end to end.
And this
one more thing to add. I guess this question comes maybe more from the temperature measurements, because there you typically want to have at least a few minutes of equilibration time. And this is something typically you don't have for batteries.
And in here, that kind of on that point, what's unique and different maybe than temperature, you have a dial, right? Which is I'm going to turn up the temperature, it's there. But here we're working with voltages and currents, right?
Yep.
So you have that control. You could set a constant voltage or a constant current and then see the response of the battery. Okay. So next question. So it's basically we require these two attachments to the D8. Is that right? So I guess what we're thinking here is we talk about the cell, we talk about the potentiostat. Now, is it available? Like if you buy it, you have to buy both pieces. Can you buy just one or the other? What do we do in that situation?
Yeah, you can buy both. You can buy one or you can buy the other.
Okay.
If you buy both, you're good to go. You can just put in your battery material and you're ready to measure. If you just buy the battery cell, then of course you don't have the option to charge your material in situ. And if you just buy the potentiostat, I think this could be actually a very interesting solution for those who are either designing their own cells for XRD or those people who are maybe using pouch cells. Because as Dennis said, you can just connect the pouch cell to the potentiostat and then drive that through our software.
Now, Dennis, after using this in the lab for a while, we had talked a little bit about windows previously. What's your feeling in terms of them being viewed as, they're consumable technically. How long do you think a Windows lasts? Is it something that somebody should buy 10 of? What's your feeling after using this in the lab?
This mostly depends on the material, I guess. So how aggressive does it interact with the beryllium window? One thing you could do, if that works for you, is put in something in between or work with electronically conducting Kapton foil, for example. I heard from customers that they do that. So seems to work. I personally haven't tested it so far. The beryllium windows we are using, they are sputtered with gold with a very thin layer. And so far, even in this water-based electrolyte, I could reuse this window several times now, and this was no issue for the window.
Okay, and in your experience, the handling of it and such, just typical lab precautions. This is a scientific device. This isn't a football or something. Take care, and it'll last, right?
Yeah, sure. Okay. Don't throw it through the lab. Don't throw it to your colleague. Give it to him really gently. With beryllium in general, there's always in the mind of people it's cancerogenic. Many materials are where people are even not aware of that. As long as you don't saw it, as long as you don't work with the dust of beryllium, it's not really hazardous. So if you treat it gently, if you have it as pure metal, as a plate, it's not really difficult to handle. Wear some gloves if you want to be safe. Don't touch it with your bare fingers. If it interacts with the sweat from your hands, then you might produce some beryllium oxide. Beryllium oxide is very well soluble, but apart from that, the beryllium itself, it's easy to handle.
Yeah.
Okay, and of course, we're going out to a global audience here, so check your local regulations in terms of disposal of that beryllium. In some areas, it does. Well, in most places, it does require a special procedure, special places that should be sent.
Yeah,
that's true.
So next question, what happens when that voltage reaches its upper limit? Does the goniometer stop and go back at its initial position to start recording a new pattern?
Good question.
That's a really good question. Christina, do you want to answer that?
No.
No? Okay, I thought you were chiming in to answer the question. Okay, then
no,
take over.
It's a question for you.
That's a good question for me. Okay. We have something called a follow-up mode. So if the segment ends and the XRD scan is still running, the potentiostat will fall back into a follow-up mode where it waits until the XRD scan has finished. Typically, this might be an issue, but since the XRD scan is really, really fast and maybe it needs 10, 20 more seconds to finish, so you typically don't set up hour-long scans, so just a few minute scans if you do this repeated experiment, then it's not an issue at all. The potentiostat will just wait in a defined follow-up mode, and then as soon as the XRD scan is finished, then it will go into the next segment and start with the next XRD method you have defined.
Mm-hmm.
All right, great. So we have a lot of people out there looking at instruments that are even smaller than a D8 Advanced nowadays. So we have that benchtop D2 phaser. So the next question is this wonderful and amazing thing available on the D2 phaser?
So I think that's a question for me.
Probably. Christina.
So in the D2, we have 2 sample holders, right? We have a 6-position sample changer, and we have a single-position sample stage. And in the 6-position sample changer, the battery cell clearly doesn't fit. In the single position, you may be able to fit it in, but you have to keep in mind the battery cell actually is a bit smaller than your normal sample holder. And it's got also a little bit of a rim to hold the beryllium window in place. And it's thicker than your normal sample holder. So I would say the short answer is it probably doesn't fit, but if you have a D2 and you want to give it a try, you may be able to get it to work. But we do really recommend to go for a D8 Advance or a D8 Discover with a rotation stage to do these experiments well.
So I guess, does the D2 have a way to get that wire in, Christina?
No.
Okay. So that's going to be the thing.
So you would only be able to measure the battery cell. You would clearly not be able to connect the potentiostat to it.
We certainly don't recommend to drill a hole inside the machine.
Yes, definitely don't be drilling.
Don't do that.
Or finding ways to run it with the cord hanging out the door. That's not a good thing.
Not a good idea.
And not possible unless you have extremely violated the system safety protocols.
John, I think maybe we should take a look before we close to the software. I think Dennis has a few things to show in EVA and in Topaz as well.
All right.
And then maybe we can take a few more questions afterwards.
Yeah, so I have prepared some scans that we recorded previously. Let's again go to the PC, and I will show you how we can evaluate it and how we can visualize it. You see the battery cell is still running. We just let it keep going. We will switch over to Diffract EVA now. This is for the visualization of the data. I've prepared a document already where we have a set of scans. This was recorded some months ago, about 140 scans. And we see here one peak which is not moving. This is actually the beryllium peak of the window. And we see a lot of peaks that are moving here, and this is the lithium manganese oxide. For every subscan, we have the information of the current and voltage. So we have all this information for every subscan available. And if we want to visualize it, like here, this doesn't look too enticing. So let's switch to something else. Let's create a 2D view. And this is much better suited to visualize what has happened inside the battery. So we see here the reflection from the beryllium window, which stays constant. We see here the moving reflection from the lithium manganese oxide. We can even change the color, make it a bit more presentable. What could be nice, inverse the color, something like this maybe. We can change a bit the contrast. So we have a lot of options to change our visualization here. Additionally to that, we might want to plot the voltage, how it has changed. We can also do that. We can activate the side view, and we can plot the voltage. So here we see how the voltage has changed. I started at about 0 volt, and then I charged the battery up to about 0.6 volt. And you see here the continuous movement, the continuous shift of the voltage by for every XRD scan. It's here numbered with the index, but we know from every scan it takes about 2 minutes. So if we multiply it by 2, we have it actually in minutes here listed up. So this is about the visualization. Now we also maybe want to evaluate that. We want to have a lattice parameter and tell someone, oh, here we have a structure change, or here we have a much smaller unit cell because the lithium is deintercalated. We want to get some actual data from this. And for that, we switch to Topaz, and we use Rietveld refinement to get all of this. We will simulate the structure, we will fit it, do a Rietveld refinement basically. I also have prepared something. Load project. Let's start with this. This was the first scan of the set, so just a single scan where I basically set up my model. Let's have a look at the refinement. I see here the lithium manganese oxide, how it has been fitted in this magenta colored curve. This additional reflections, I have fitted them with fixed peaks, so they will not bother me in any way. I can deconvolute the structure from the rest, and I can actually see what my material is doing. Now I will take this model as a basis for my additional evaluation. So I have scanned 140 scans. So I replace the scan, refine the next one, I replace the scan, refine the next one. If I do this 140 times, it takes me 2 afternoons and a lot of coffee to get all of my data. With Topaz, we don't have to do it manually, fortunately. We can do a parallel refinement. We use this model I have set up here and just copy paste it to all of the other ranges. And with Topaz, we can do a parallel refinement of all of these 140 ranges. I click here, I take the initial model, and Topaz will calculate the shift and the lattice parameter for all subsequent scans. Let's have a look. And it applies it here. And this took about 3 seconds. On a faster PC, this will, of course, go really even faster, but I think 3 seconds is quite acceptable for fitting of 140 ranges in parallel. Let's zoom in on one of the reflections here, maybe. And you can see for every single range how the reflections have shifted. Zooming out again. And I can, of course, also get the information about the lattice parameter, for example. So we started here in the first range with a lattice parameter of 8.21 angstrom, and then the lattice or the yeah, the lattice parameter decreased down to 8.16 angstrom. I can copy this now, put it into Excel or into any other program and visualize it. I can calculate from the cell volume, maybe the lithium content. I can visualize all the things I need now. So Topaz allows you to fit all of this multi-range data you produce with the battery cell.
That is pretty nice. Thank you, Dennis, for
Definitely.
Software demo. What I also like is that it's pretty stable, right? I mean, maybe here your peaks are shifting a little bit and it's maybe relatively easy for the program to fit the data. But I remember really fitting temperature data, one temperature set after the other, really fighting with that software to control the parameters. And I think that's really one thing I love about Topaz, how quick, how stable it is. And it's just fun to use.
Yeah, that's true. It stays very stable. So even if you're quite off with your initial guess, with your initial parameters, it usually still finds the correct parameters and does a pretty good job at refining the data.
Yeah.
And here we definitely, I think, see that benefit of having that full integration with the data, having the values stored in it, right? And things like that.
Yeah, exactly.
Yeah.
All right. So with that, I think we are going to bring in Norman here.
Hello.
And,
right. I'll head back to the machine.
And yeah, Dennis will head over by his instrument. So kind of to wrap things up, like I said, a lot of exciting things on the XRM scale. We can really see how it's beneficial to the battery analysis. XRD, especially with this new integration, really seems to bring in that microstructure to it. So maybe some closing thoughts as we go around the room here. Let's go ahead and let's start with Dennis about kind of the integration, what it's like to use it. Some of your final thoughts on that.
Yeah, it's actually quite easy to use. Maybe at first you might think this table format is maybe a bit complicated, but you get used to it very quickly. I showed it to many people now and everyone was able to do it himself after just a few minutes. You just need to know that there are a few buttons that you need to press and then you have your segments that you need. It's really rather simple to use.
All right, great. And then Norman, on the X-ray microscopy side, maybe a few thoughts about battery work being done in some of these benchtop and X-ray.
As you could see on the XRM demo, it was quite easy to set up a scan. Also, the sample preparation is quite easy because it's touchless. So because X-rays just getting through the sample, so the sample preparation is just put it on the sample holder, glue it a little bit tight, and that's all. And XRM gives you a great opportunity to observe, to analyze your sample in 3D. So, yeah.
Great. And, you know, another nice thing there is that we're supporting it all the way from the research stage through final production, right? I mean, being able to actually analyze those cells as they are being used out in the real world.
Yeah, absolutely. So we have a good opportunity to support your R&D department. Also later in the production to overwatch, to make a random sampling, to check if any parameter as a production is okay or run out of the tolerance.
All right. So the next time that my laptop battery decides to blow up, I think I'm going to be sending it over to you, and we're going to get down to it.
Yeah.
And then maybe Christina, maybe some thoughts about this XRD solution.
Yeah. So also from my side, what I think is really exciting is to have the control of your experiment. I think it's always nice to be in charge and to charge your batteries. And what I like also about the combination of XRD and XRM is that we're covering actually quite a big part of the life cycle of the batteries, right? So XRD you could really use at the start, raw materials control, maybe process control of cathode materials in a production setting. Then you can take it to the research stage where you're looking at new materials. And of course, with XRD, you look at the atomic structure. You can also look at crystallite sizes. And that kind of transitions over to the XRM, where we then look at the microstructure. And I think it's really nice to cover those different length scales and the different parts in the life of a battery with these different techniques.
So, and I think with that, you know, the important thing to understand is that all of these things are simply an additional tool that a researcher has, whether that's an X-ray microscope looking at that macrostructure, the microstructure from XRD, or even other techniques. And, most importantly, I think what we've learned today from all of these experts is it takes that knowledge too, something that's quite indispensable. You can never replace that with an instrument or a tool. So to all those people out there who are doing battery research, you, of course, are one of the most important parts of these experiments. And what you see here, hopefully, in our Bruker solutions is that our goal really is to support your discoveries moving through and into the future, making sure that these solutions hopefully are easier to use, enabling you to do that work and spend less time doing those sorts of things. So until next time, we will see you then. Goodbye.
Take care.
Yeah.
Bye-bye.
Thank you. Take care.
Bye-bye.
Goodbye.